All right, the next topic that we have within this section is the curl operator. Much like the divergence operator, we can think of the curl as a type of derivative. It's a way of taking in a vector quantity, a vector field, and producing because the output of this is actually, if you see the I, J, and K hat, this output is a vector. So in particular here, the curl of let's write this in red here. This is the curl of a vector is a vector. Whereas the divergence of a vector is a scalar. So two different types of derivatives, two different ways of producing a quantity that somehow encodes the rate of change in a certain sense. So in the previous video, we talked about conceptually and geometrically what the divergence is telling us of a vector field. So what exactly is the curl telling us of a vector field? Well, given a vector field, the vector fields is really, you can think of this as a series of arrows. Now, in general, in actuality, a vector field is a infinite collection of these arrows, all with their own directions and lengths. But we can sort of imagine stitching together these arrows to form a curve or a flow, so to speak. Okay? Much like if you had a positively charged particle, you would imagine the field lines coming out like this, something like that. Or if you had a positive and a negative charge, how you would have these field lines coming out like this. Right? And then you'd have to interpolate in between, stuff like that. So you can think of these vectors, these individual discrete little vectors with their own directions and lengths being stitched together to form this flow or current, so to speak. And, what can sometimes be lost by the stitching together to form this one stream is that you don't always get a sense of the strength of the vector field. That's why the length of the arrows of the individual vectors are important. You could have something where it is quite, getting stronger or something like this, and then, the sense is that if you had something here that, because it's being pushed less down here on this end and it's being pushed more on this end, this line segment here would sort of rotate or curl. So think in your head, think of the edge of a riverbank. So on the edge of a riverbank, depending on how the riverbank is, maybe curved or something like that, the stream's coming down this way, okay? But what happens is the current kind of comes in here a little bit, and then what can happen is in this area, you sometimes get this rotational character where you just see the water and the different debris, whether it's leaves or foam, foam, different bubbles, things like that. They sort of collect because they start to rotate around the edge there. Well, given a flow or a vector field, certain regions there might be this propensity to rotate maybe. And what the curl actually does is when you have a vector field and you have a point, so let's call this vector field F. If you take this point P, the curl of this vector field F at the point P, this produces a vector, so I'll just say V for vector. It produces some vector, and this vector effectively gives you the axis of rotation. So if this river that I just drew here, this flow, if this were in the xy plane, and we had a point and it was rotating this way, then the axis of rotation would be, using your right-hand rule, out of the board or out of the screen. Imagine the vector v is coming directly out of the screen from this point. Now the length of this vector v, the length of the curl, the magnitude of the curl, would essentially be that rate of rotation, or at least proportional to it. So the curl, in short, is a way of quantifying whether or not, or I guess we can say, the rotational character of your vector field. So at a certain point, is your vector field, how much is it rotating? How rotatey is it at a specific point is effectively what the curl is telling us. And not only that, it also tells us what the axis of rotation is. If the vector is very short, then it might not be rotating very much, but it still kind of has a little bit of a rotation, and the length of the vector tells us that it's not a lot, but the direction of the vector tells us that orientation, the direction of the axis of rotation. Okay. Example 3, determine the curl of the vector field f. So to determine the curl, if we kind of go back for a second here, kind of glossed right over that, the curl is effectively, I mean, it is a cross product, as you can see, this cross f. So we can do our usual determinant here, but the main thing is we have these instructions to take the appropriate derivative along the middle. So I don't urge anybody to memorize this. I urge you to have this memorized and then use that to compute this. If you are struggling with this or need a little bit of a refresher, I'd go back to 12.4, which is the cross product, and you can review cross products, because really that's all the curl is. It's a cross product with this as your middle row. So to compute the curl of f, so curl of f is, you can draw our determinant here. We have our x partial instructions, y and z, and then we have our components. So xy, e to the x, y plus z. Taking this, we'll have, we're going to do, remember, we're deleting this, and then what's left over is this sub-determinant, and then we're going to do this times this. So effectively, we're going to take the y partial of this, and then subtract the z partial of this. So this will be 1 minus 0 times I hat, minus, because remember, we always alternate plus, minus, plus. So we're on the minus term. We're going to do the, so we're deleting it like this. So we're left over with these 4 entries. So with that, we're going to take the x partial of this term, which is 0, minus, we're going to do the z partial of this term, which is 0. J hat. Plus, we're back to plus. We're now deleting the third column along with the top row. So we have the y partial of xy, so that's just x, minus the x partial of e to the x, which is e to the x, k hat. So the curl ends up being 1, 0, e to the x.